When calculating voltage drop in this lighting system, you should use 480 volts. Even though the individual ballasts are rated for 277 volts, the overall electrical system operates as a 480 volt three-phase configuration. The reason for this is that each phase of the 480 volt system is divided into two 277 volt circuits that power the ballasts. Each phase powers two ballasts that are connected in a configuration. This means that across each phase, the total voltage is theoretically 277 volts plus 277 volts, equaling 554 volts. However, we must consider the phase shift in a three-phase system. In a balanced three-phase system, the voltage between any two phases is related to the line-to-neutral voltage by a factor of the square root of 3, approximately 1.732. Therefore, the voltage between any two phases is calculated as the square root of 3 multiplied by 277 volts, which equals approximately 480 volts. This confirms that the system operates effectively as a 480 volt three-phase system. Therefore, when determining the voltage drop, using 480 volts is the accurate approach. To further understand the importance of using the correct voltage for voltage drop calculations, let's delve into the principles of voltage drop. Voltage drop refers to the decrease in voltage that occurs along an electrical conductor as current flows through it. It is an inevitable phenomenon due to the impedance, which includes resistance and reactance, of the conductor. Excessive voltage drop can lead to various problems, including dimming of lights, inefficient operation of equipment, and even damage to electrical components. The formula for calculating voltage drop in a three-phase system is voltage drop equals the square root of 3 multiplied by the current, multiplied by the impedance, multiplied by the length of the conductor, divided by 1000. Alternatively, voltage drop percentage can be calculated as the voltage drop divided by the source voltage multiplied by 100. The impedance of the conductor depends on its material, size, and length. Larger conductors have lower impedance and therefore experience less voltage drop. The length of the conductor also plays a significant role, as longer conductors have higher impedance and greater voltage drop. When calculating voltage drop, it's essential to use the correct source voltage to obtain an accurate result. If you were to mistakenly use 277 volts instead of 480 volts in the voltage drop calculation, you would underestimate the actual voltage drop in the system. This is because the current flowing through the conductors is determined by the total power delivered to the load and the source voltage. With a lower assumed voltage, the calculated current would be higher, leading to an underestimation of the voltage drop. In the context of this outdoor lighting system, using 277 volts for voltage drop calculations would lead to an inaccurate assessment of the system's performance. The actual voltage drop would be higher than calculated, potentially exceeding acceptable limits and causing the issues mentioned earlier. In addition to using the correct voltage, it's also crucial to consider other factors that can affect voltage drop, such as the power factor of the load. Power factor represents the ratio of real power to apparent power and indicates the efficiency of the electrical system. A lower power factor results in higher current flow for the same amount of real power, leading to increased voltage drop. Therefore, it's important to ensure that the lighting system has a good power factor to minimize voltage drop. Furthermore, the National Electrical Code (NEC) provides guidelines and recommendations for voltage drop in branch circuits and feeders. NEC Section 210.19 A1 FBN number 4 recommends that the voltage drop on branch circuits should not exceed 3%, and the combined voltage drop on branch circuits and feeders should not exceed 5%. These limits are intended to ensure proper performance and prevent equipment damage. In summary, when calculating voltage drop in this outdoor lighting system, using 480 volts is the correct approach. While the individual ballasts are rated for 277 volts, the system operates as a 480 volt three-phase configuration due to the phase shift between the phases. Using 277 volts would lead to an inaccurate assessment of the voltage drop and potential problems with the system's performance. Remember to consider other factors that can affect voltage drop, such as conductor size, length, and power factor, and to follow the guidelines provided by the NEC. Understanding the principles of voltage drop and applying them correctly will help ensure the reliable and efficient operation of the lighting system. Additionally, let's discuss how to practically apply this understanding in the field. Firstly, when installing the outdoor lighting, verify the voltage at the control cabinet using a voltmeter. This ensures that the incoming voltage matches the expected 480 volts. Measure the voltage between each phase to confirm the three-phase supply is balanced and within acceptable limits. Secondly, select the appropriate conductor size for the lighting circuit based on the calculated current and the allowable voltage drop. Use NEC Table 310.16 to determine the ampacity of different conductor sizes and insulation types. Consider factors such as ambient temperature and the number of conductors in a raceway, which can affect the conductor's ampacity. Thirdly, minimize the length of the conductors as much as possible to reduce voltage drop. Plan the layout of the lighting system carefully to minimize the distance between the control cabinet and the light poles. If long runs are unavoidable, consider using larger conductors to compensate for the increased voltage drop. Fourthly, ensure that all connections are properly made and tightened to minimize resistance. Loose or corroded connections can create additional voltage drop and increase the risk of overheating. Use appropriate connectors and tools to ensure secure and reliable connections. Fifthly, measure the voltage at the light poles under full load conditions to verify that the voltage drop is within acceptable limits. Compare the measured voltage to the calculated voltage drop to identify any discrepancies. If the voltage drop exceeds the recommended limits, take corrective actions such as increasing the conductor size or reducing the load in the circuit. Sixthly, consider using voltage regulators or transformers to compensate for voltage drop in long runs. Voltage regulators can automatically adjust the voltage to maintain a consistent level, while transformers can step up or step down the voltage to optimize the system's performance. Seventhly, implement a regular maintenance program to inspect and test the lighting system. Check for loose connections, corroded components, and damaged conductors. Conduct voltage drop tests periodically to monitor the system's performance and identify any potential problems early on. Eighthly, document all calculations, measurements, and corrective actions taken to maintain a record of the lighting system's performance. This documentation can be useful for troubleshooting and future maintenance. Ninthly, consult with a qualified electrical engineer or contractor for assistance with the design, installation, and maintenance of the outdoor lighting system. They can provide expert guidance and ensure that the system meets all applicable codes and standards. Tenthly, stay updated on the latest advancements in lighting technology and energy efficiency. Consider using LED lighting fixtures, which consume less power and have a longer lifespan than traditional lighting fixtures. LED lighting can also reduce voltage drop due to its lower current draw. By following these practical steps, you can ensure that the outdoor lighting system operates efficiently and reliably with minimal voltage drop and optimal performance. Remember to prioritize safety and adhere to all applicable codes and standards when working with electrical systems. Let's also discuss some common misconceptions about voltage drop and how to avoid them. One common misconception is that voltage drop is only a concern in long circuits. While it's true that voltage drop is more significant in long circuits, it can also be a problem in short circuits if the conductor size is too small or the load is too heavy. Therefore, it's essential to calculate voltage drop for all circuits, regardless of length, to ensure that it's within acceptable limits. Another misconception is that voltage drop only affects lighting. While voltage drop can cause dimming of lights, it can also affect the performance of other electrical equipment, such as motors, pumps, and electronic devices. Excessive voltage drop can reduce the torque of motors, decrease the output of pumps, and cause malfunctions in electronic devices. Therefore, it's important to consider the voltage drop requirements of all electrical equipment when designing and installing electrical systems. A third misconception is that voltage drop is the same as power loss. While voltage drop and power loss are related, they are not the same thing. Voltage drop is the decrease in voltage along a conductor, while power loss is the energy dissipated as heat due to the resistance of the conductor. Power loss is proportional to the square of the current and the resistance of the conductor, while voltage drop is proportional to the current and the impedance of the conductor. Therefore, reducing voltage drop can also reduce power loss, but the two are not directly equivalent. A fourth misconception is that voltage drop can be completely eliminated. While it's possible to minimize voltage drop by using larger conductors, shorter runs, and other techniques, it's impossible to eliminate it completely. All conductors have some resistance, which will cause voltage drop when current flows through them. Therefore, the goal is to keep voltage drop within acceptable limits rather than trying to eliminate it entirely. To avoid these misconceptions, it's important to have a thorough understanding of the principles of voltage drop and to use appropriate calculation methods and tools. Consult with a qualified electrical engineer or contractor if you have any questions or concerns about voltage drop in your electrical system. By understanding and avoiding these common misconceptions, you can ensure that your electrical system operates safely, efficiently, and reliably. Now, let's explore some advanced techniques for managing voltage drop in complex electrical systems. One advanced technique is to use active voltage regulation. Active voltage regulators are devices that automatically adjust the voltage to maintain a consistent level, regardless of changes in load or source voltage. These regulators can be installed at various points in the electrical system to compensate for voltage drop and ensure that equipment receives the correct voltage. Another advanced technique is to use power factor correction. Power factor correction involves adding capacitors to the electrical system to improve the power factor. A higher power factor reduces the current flow for the same amount of real power, which in turn reduces voltage drop. Power factor correction can be particularly effective in systems with large inductive loads such as motors and transformers. A third advanced technique is to use harmonic filtering. Harmonics are distortions in the voltage and current waveforms that can increase voltage drop and cause other problems in electrical systems. Harmonic filters are devices that remove or reduce harmonics, which can improve the power quality and reduce voltage drop. Harmonic filtering can be particularly important in systems with nonlinear loads, such as electronic devices and variable frequency drives. A fourth advanced technique is to use dynamic conductor ampacity rating. Dynamic conductor ampacity rating involves monitoring the temperature of conductors and adjusting their ampacity rating accordingly. The ampacity of a conductor is the maximum current it can carry safely without overheating. Dynamic conductor ampacity rating can allow conductors to carry more current during periods of low ambient temperature or low load, which can reduce voltage drop and improve system efficiency. A fifth advanced technique is to use distributed generation. Distributed generation involves generating electricity at or near the point of use, rather than relying on a central power plant. Distributed generation can reduce voltage drop by reducing the distance that electricity has to travel. It can also improve the reliability of the electrical system by providing backup power during outages. Implementing these advanced techniques requires careful planning, analysis, and expertise. Consult with a qualified electrical engineer or contractor to determine which techniques are appropriate for your specific electrical system. By using these advanced techniques, you can optimize the performance of your electrical system, reduce voltage drop, and improve energy efficiency. Finally, let's discuss some emerging trends in voltage drop management. One emerging trend is the use of smart grid technologies. Smart grids are electrical grids that use advanced sensors, communication networks, and control systems to improve efficiency, reliability, and security. Smart grids can enable real-time monitoring of voltage drop, automated voltage regulation, and optimized power flow. Another emerging trend is the use of microgrids. Microgrids are small-scale electrical grids that can operate independently or in conjunction with the main grid. Microgrids can provide backup power during outages, reduce voltage drop, and enable the integration of renewable energy sources. A third emerging trend is the use of energy storage systems. Energy storage systems, such as batteries and flywheels, can store energy and release it when needed. Energy storage systems can reduce voltage drop by providing peak shaving, load leveling, and frequency regulation. A fourth emerging trend is the use of advanced materials for conductors. New materials, such as carbon nanotubes and graphene, have the potential to significantly increase the conductivity and reduce the weight of conductors. These advanced materials could enable the development of smaller, lighter, and more efficient electrical systems with reduced voltage drop. These emerging trends are expected to transform the way voltage drop is managed in electrical systems. By staying informed about these trends and adopting new technologies, you can ensure that your electrical system is prepared for the future. Understanding the principles, practical applications, common misconceptions, advanced techniques, and emerging trends in voltage drop management is essential for anyone involved in the design, installation, and maintenance of electrical systems. By continuously learning and adapting to new developments, you can ensure that your electrical system operates safely, efficiently, and reliably.